Hi, good morning. So as I said, my name is Russell Binions from University College London. I'm going to tell you something today about a hybrid chemical vapour deposition to make golden vanadium dioxide nanocomposites, which we're going to show how they work in smart window systems. So first of all, why are we interested in smart windows? Well, if we have a look at the solar spectrum, as here we can see that a lot of energy is able to permeate through a window, both in the visible, the near infrared and the far infrared. We spend a lot of money each year heating and air conditioning our buildings, and this obviously doesn't help in our fight against global warming. So if we can develop some strategies to limit the amount of heat that can enter or leave a building, then we should be able to save some money and energy in the process. So how's this done to start with? Well, the current conventional approaches have static approaches, so that's the films or the windows have fixed properties, and they are typically heat mirrors which strongly reflect in the near infrared, and they typically just prevent energy from entering a building. Not so good at preventing black body radiation from leaving the building. And they're normally sputter-coated thin films of metals such as silver or gold. They can be quite complicated and difficult to make. It's an offline process, so you have another step in the manufacture. Low emissivity coatings are highly reflective in the far infrared, and they basically prevent black body radiation from escaping a building. So this is ideal in cooler climates like in Northern Europe or in the very southern hemisphere. Basically helps keep your building warm, cuts down on your heating costs, and things like that are things like fluorine-doped tin oxide, or such as the Pilkington product K-glass. The other example is an absorbing glass, and typically these are body tinted, and they absorb near-infrared radiation and prevent it from entering a building. And they're very useful, but they're typically very difficult to make. You have to control the melt in your float glass line, and it can be an extremely difficult process. Okay, so here's some example spectra. The top left is our sputtered coating. You can see the reflectance, the red line. It's very high in the near infrared. Basically gets rid of all of the solar radiation before it is allowed to enter the building. Bottom left is a low E coating. So you allow a large amount of visible and near infrared light through, but you're starting to see the reflectance creep up in the far infrared, and the far infrared extends right along to up to 50 microns, where the reflectivity is about 85%. This one in the top right is typical of a normal piece of glass. In this case, it's been coated with Pilkington Active, which is a self-cleaning coating. Doesn't have any energy saving properties as such, but it gives you an example of the reflection and transmission for a normal piece of glass. And bottom right is an absorbing glass. In this case it's a blue glass called Arctic Blue, which absorbs very strongly. It's not very reflective, but it's very strongly absorbing. Okay, so Daisy. So we're going to talk about thermochromic glazing, and basically what this means is that we have a type of material. We use vanadium dioxide. It has a phase transition, so when it's a lower temperature we have a monoclinic phase, which is semiconducting, so it's not reflective at all in the infrared. Hence in our cold lab in London, lets all of the heat energy in, and we're able to have a nice comfortable working environment. Similarly, in hot weather, the temperature or the coating above a certain temperature, which we can tune, becomes more reflective, so a portion of the solar energy is reflected away, and we're still able to maintain our same comfortable working environment. Okay, so we're talking about making nanocomposites. It's well known that you can make vanadium dioxide and that you can tune the transition temperature to anywhere between the standard 68 degrees right down to below to about minus 40 degrees, which is obviously a bit more than we'd want. But so why nanocomposites? Why are we interested in gold in particular? Well, gold, as you'll all know, as a nanoparticle, has a surface plasmon resonance. It has a strong absorption. So we can hopefully use this to improve our properties, as well as having a phase transition. So we have a variable heat mirror. We also hopefully have a strong absorption as well. So how are we going to do this? Well, we'll have our standard atmospheric pressure chemical vapor deposition set up, but we'll also have a humidifier and an aerosol system, so we can generate an aerosol of gold nanoparticles in methanol. Typically we just use auric acid and methanol, and then we'll mix this with our atmospheric pressure flow of vanadal-Akak in a flow of 2% oxygen. Okay, this is what the equipment looks like. So you can see our atmospheric pressure CVD set up here, bubblers, mixing chamber, and here we have our aerosol system. You can't see the humidifier very well. We basically just mix the two in a special manifold, and this all goes into a deposition chamber reactor, which is set to 525 degrees Celsius, which is high enough to avoid any problems with carbon contamination, because everything basically burns very cleanly at that temperature. Okay, so make some films. Here's a typical example. So on the left, A is a secondary electron image, and B is the corresponding backscattering image. So you can basically see that the gold goes absolutely everywhere amongst the crystals, and there's a very wide distribution of particle sizes. We can confirm this with X-ray diffraction. You can see we've got our VO2. Typically these films are about 100 nanometers thick, so they're quite thin, hence we see a broad amorphous hump. But we do have a couple of peaks which relate to gold. Using the Schur equation, we can work out that our crystallites are around 10 nanometers in size, but they're quite, as I say, there's quite a dispersion. If we look at some X-ray photoelectron spectroscopy of the surface, we again see that we've got one nice gold environment, very symmetrical peaks, which tells us that basically the gold is just there as crystallites. There's no doping as such. If we look at the vanadium and oxygen environments, we see that there's more than one environment there. And as this is the surface, we come to expect this. We expect there not only to be vanadium in a +4 environment for VO2, but some extra oxidation to V2O5, and that's reflected there. And this is very common and well known. So if we look at the optical properties, if we look at A, this is transmission behaviour. This is quite a thick film, hence the transmission is very low in the visible. But the important thing is it doesn't change very much. There's a slight shift in the centre, and this is to do with the changing environment of the gold nanoparticles. As you go from your monoclinic to your rutile phase, you see a corresponding change in the dielectric constant of your matrix, and this leads to a different centre for the surface plasmon resonance absorption. But we'll talk about that in the next slide a little bit more. But what we can see is we see a big change in the infrared in transmission as we go from the cold phase, or the monoclinic phase, to the rutile phase. If we look at the reflection behaviour, the transition isn't so big, and this is partly due to the fact that we've got quite a lot of gold in there, so our films have a more metallic character anyway.